I'm Maddie.
And our extension project was on the solubility product through spectroscopy.
So in this extension, we found the concentration of an unknown using spectroscopy, and we measured the wavelength that had the best absorbency for copper sulfate and ammonia, and we also found the stock molarity of the Cu2+, and we created 4 additional solutions and found the molarity of those as well. And then we found the absorbency of each solution of the Cu2+ using the microlab. And this was different from the original experiment because there was no spot testing done or mixing of various acids and bases to find what ions are formed. So this is our first data table. On the left, those are the 5 solutions that we did, and it's basically dilution of the Cu2+, and then slowly ammonia is added, and then on the right are all of the different molarities that we found.
And this is our second data table, and it's using the same 5 solutions, but here we are measuring the absorbency through spectroscopy using the microlab.
And using our last data table, we graphed absorption on the y-axis versus the molarity of the solution on the x-axis. And after fitting a trend line to the graph, we found that the relationship between absorption and between molarity was a positive correlation, which means that whenever absorption increased, the molarity also increased. This is because of the Beer-Lambert law, which states that absorption equals the molar absorptivity of a solution multiplied by its path length times the concentration sample. Or more simply, but when the concentration of a solution is increased, less light is able to travel through the solution, which means more light is absorbed, increasing the absorptivity. And in this experiment, we made 4 different calculations. So we calculated the molarity of the copper 2+ stock. We found the value of x from our equation using the graph. We calculated the solubility product, and we calculated the percent error. To find the molarity of copper 2+, we used the equation M1 times V1 equals M2 times V2, which is the dilution equation. And using this value that we calculated, we were able to calculate the x value from our graph, also using the equation from our graph. And then using that value, we were able to calculate the KSP, which is the solubility product, which means it's the product of the dissolved iron concentrations. In this case, it was copper 2+ and CO3 2-. And since they had a 1-to-1 ratio, the stoichiometric coefficients in front of the 2 ions were 1-to-1, which means we just ended up doing 0.72 squared to find our value.
So after we found the KSP value, we looked up the actual KSP value for CO3, and we calculated a percent error. The percent was pretty high, so the results were the best, but I think it was based off of, we weren't sure which absorbency we should choose, and that messed with the graph, which caused our experimental value to be wrong. The sources of error that we found were measurement inaccuracy, which can be fixed by using better tools more appropriate to get a more accurate measuring out of the certain values, and then the calorimeter did basically all of the work for us, and it found the absorbance of each solution for us, so we used the numbers that were cranked out by that machine. One thing that was really different about the lab, the original lab and the extension, was the KSP value, which is the solubility product. And that was basically what was the biggest difference, besides the fact that we used the microlab instead of mixing acids and bases to pull out different ions and then spot testing.
So spectroscopy is used pretty frequently in the real world. Some examples are to characterize proteins, to monitor dissolved oxygen content in marine ecosystems and in freshwaters. It's also used for respiratory gas analysis in hospitals, and it's used to study spectral emission lines of distant galaxies. So because we can't easily travel to distant planets, we can't find which type of molecules are present in particular samples. So instead, we use mass spectrometers to identify miniature particles that are present in space. And this allows us about space and about these particles that are present there without having to actually go there, so it saves us a lot of money.
So the conclusions, it's just the findings that we found from the extension. So overall, we found the unknown molarity of the compound using the microlab. The overall experience of the extension was pretty good. It was easier to follow, the directions were pretty straightforward. And then future suggestions for other people is just to be careful of measurements, just to make sure that everything is pretty accurate, otherwise the absorbencies can be